So dear students, in today's topic, we are going to see about various types of activation functions that can be used in the design of neural network. Okay, so what is an activation function? To provide non-linearity to your model, which is need of the hour if you're working with any real-time data or real-time model, you require activation function. You have seen how come linear model was insufficient and what is the need for non-linearity in a particular neuron model. So to adapt to non-linearity and to take up any logical decisions, you require an activation function. So an activation function is a deceptively small mathematical expression which decides whether a neuron fires or not. You have also seen that we are using several layers of neurons throughout the neural network, and we know that almost all of them are interconnected. But if you really want to understand whether the next neuron in the next layer is supposed to be fired or not, you are supposed to design suitable activation function on it. So based on that logical mathematical expression, you are going to decide whether the next neuron is going to fire or not, whether there can be an interconnection formed between the two layers or not. So that's basically the work of an activation function simplified. So activation function is a deceptively small mathematical expression which decides whether a neuron fires or not. It provides significant improvement in performance of a neural network, and you have got different types of activation functions. The first one being linear transfer function, Heaviside function or a step function, Softmax functions, ReLU, Leaky ReLU, Hyperbolic tangent function, or in short that we call it as a tan-H function, Sigmoid function, or the other name is logistic function. So we are going to see each of them in detail. The very first being very simplest of all, the linear function. So as the name suggests, the linear transfer function is something like an identity function, and you can see over here the signal passes, this is your linear transfer function that you can see it comes as a straight line. So that's what the name is, an identity function. Identity function in the sense the output is going to be same as an input. So that's the mathematical function fit. The output f of x is going to be the same as input x. So that's how the output remains unchanged. It is going to be same as an input at that step of time, and it is normally do not use much because we do not want the output to be same as input. There has to be something that the output is supposed to be manipulated version of input in real time. So yeah, this is an ideal type of a function, the very first function, linear transfer function, for your knowledge. Now, the second function is the step function. The other name is also Heaviside function. It is also called as a binary classifier. Now, the moment I say binary classifier, it can be used to produce an output of either 0 or 1. So, you can see for that reason, after 0, for all the positive values of input, you have got the value as 1. For all the negative sides of the input, you have got the value as 0. So it is going to give you a discrete value. So that's how I write, if your total, that is your W or weight multiplied by input plus bias, that's what we write as a mathematical expression in a neuron model. So if this is not triggering, that is if it is negative, if it is less than or equal to 0, then the output is going to be 0, otherwise output is going to be 1 if Wx plus b is a positive value. So you will be knowing whether to trigger that particular neuron or not. So basically useful in binary classification to obtain a discrete value of either 0 or 1. That is step function for you. The next function is a sigmoid function. You can see sigmoid function is an enhanced function of a unit step function. So the step function you were seeing, it was very abrupt, in real time you cannot have such an abrupt function. That's the reason you go for a sigmoid function, a little better version. So the other name for it is a logistic function, because it is again useful in logistic regression. That is nothing but your again binary classification. So what is the difference between now the step function and this function is, step function abruptly gives you the value of 0 or 1, whereas the sigmoidal function, it is going to squish all the values of probability between 0 and 1. That means what is the probability of the value being 1, what is the probability of value being 0. That's how it is not so abrupt when you plot. plot it. Okay, so it reduces the extreme values or outliers in a particular data, and it is obviously useful in a binary classification. Now coming to the mathematical equation, we write it a sigmoid function actually as a sigma, and the mathematical expression is 1 plus e power minus z. So this is something which you are going to remember. So here is also a sample code I have written here if you want to create a sigmoid function, but since you are using TensorFlow with a Keras API, all of these activation functions are inbuilt. You need not write a separate code for it. Just remember what for it is used, how it looks like, and what is the mathematical expression, and they are important in terms of exam also. Now the next type of a function is a softmax function, right? So I told you the step function or sigmoid function, they are specifically used for binary classification. That means when you have got a classification of only two classes, whether 1 or 0, when you have got two classes. Now what about when you have a multi-class classification? So in that case, you are supposed to use a softmax function. So what is softmax function? It is nothing but a generalization of the sigmoid function. It is used to obtain classification probabilities when you have more than two classes. And now coming to the mathematical expression, since I have more than two classes, I am writing input as xj, again sigmoid of xj, and this is equal to, this is equal to e power xj by summation over j and e power xj. So this is going to be the mathematical expression for your softmax function. So this was about sigmoid softmax function. Now the next type of activation function is the tan h function. So we call it also as a hyperbolic tan h function. So what is going to be the range of tan h function? The range of tan h function is going to be from -1 to 1. So when you want to squish all the values in the range of -1 to 1, then you have to go for tan h function. And mind it, tan h functions are mostly used in hidden layers. When you are even expecting the output of to be negative for a certain layer, and for that reason in the hidden layer you go for a tan h function. It works better than a sigmoid layer, but in hidden layers. Okay, so sigmoid function, you know, it works better than sigmoid function in the hidden layers. So when I say tan hyperbolic function, so very quickly I am going to write it down. Tan hyperbolic function mathematical expression, the range is from -1 to 1, and the form, the mathematical expression is e power x minus e power minus x, e power x plus e power minus x. So you can see very clearly the shape is of a sigmoid here, but when you see the range is from -1 to 1. So for squishing all the values of the output of a layer from -1 to 1, you are going to make use of a tan hyperbolic function. Next, very important function, ReLU function. ReLU stands for rectified linear unit. The moment when I call rectified, that means I am doing certain sort of rectification to that particular waveform. Okay, so what is the rectification that you are able to see? You are able to see that I am truncating this particular waveform in the negative values, and then I have a straight line towards the positive side. So that's a ReLU. So what is happening inside a ReLU? It activates a node only if the input is above 0. So if the input is above 0, then the node is activated. Okay, so that's why ReLU is also useful in hidden layers. When you want to have interconnections between several neurons inside hidden layers, then you would see that if the previous node or previous neuron was triggered or not, and then you want the next neuron to be triggered, interconnected to it or not. So if the input was more than 0, then the next neuron is also going to fire. So for that you are going to use a ReLU. So it activates a node only if input is above 0, and it is recommended for hidden layers, and it is far better than tan hyperbolic function. So when you see the waveform, you could say that for any value which is less than 0, it is 0. For any value above 0, then it will give you the maximum value between 0 and that particular input. Okay. So if input is 0, it is not going to fire, otherwise it is going to give the same value as input. So this was about ReLU function. Now as we move on more specifically, designing more neural networks, you will be seeing where do I use this activation function based on what type of application. Now a little modified function of ReLU is a Leaky ReLU. So ReLU was more idealistic. Instead of having the function to 0, when there were negative values of the input, leaky ReLU, what it gives you is gives you a very small negative slope, which will be around 0.01 whenever you have input negative. So we are not drastically putting the output as 0 when there is an input negative, when there is a negative input heating. But we are trying to make it a very realistic version wherein you give a value of small value of 0.01. So you could see a little change here in the slope, which was not previously. So you can see previously you have got a straight line, here you have got a little slope. So that's why the mathematical function also changes. Now we are going to write f of x as, instead of max of 0 comma x, we are going to give a small value to it, 0.01 into x and then x. So that's how you get a very small value of the output even if the input is less than 0. That was about Leaky ReLU. So this was about various types of activation functions and where to use them, how to use them. Subsequently, when we move into the course, we are going to see their uses.